Welcome to Brain Vision.
In this question, we want to find what is the energy released by this reaction, this nuclear fission of uranium to strontium and xenon. So to find the energy released, we need to find the Q value, that is defined as the change in the masses of the nuclide multiplied by C squared. The change in the mass is simply taking the initial total mass of the reactants subtracted by the final mass of the products. So we have mass of uranium plus mass of the neutron subtracted by mass of the strontium, mass of xenon, and 12 times the mass of neutron. Right? We have 12 neutrons as our final product. Multiply everything by c squared, and we should get the answer. So the masses are already given on the right hand side here. You can find them from Appendix B. Since they're in atomic mass units, right, we can use c squared in the form of nitrogen 1.5 MeV per U, right, which is a more convenient form since we are dealing with atomic mass units, and we can get the energy in terms of MeV more conveniently. So the final answer, we should get 126.5 MeV by just substituting all the values, right, on the right hand side into the equation.
Welcome to Brain Vision.
So for this question, we're given that we have a reactor that is producing power of 240 megawatts. We want to find how many fissions is actually occurring, right, per second to obtain this level of power. So the energy per fission is given to be 200 MeV. But since we are dealing with megawatts, right, which is in terms of joules per second, we have to convert this into joules by multiplying by 1.6 times 10 power minus 13 joules per MeV. Following this, we should be able to get what is the number of fissions per second by taking the power divided by the energy per fission. Right, since the power tells us the energy released per second, so we should be able to get what is the number of fissions per second. So this is 240 times 10 to the power of 6 joules per second. Divide that by our previous expression on top. And we should get about 7.5 times 10 to the power 18 fissions or reactions per second.
Welcome to Brain Vision.
So we are given that uranium-235 undergoes fission reaction to produce 200 MeV of energy approximately per fission reaction. Now to find what is the fraction of the mass, we need to look at the rest energy, right? So the rest energy is defined as mc squared. In our case, the mass of the uranium-235 is 235U multiplied by c squared, which is given as 91.5 MeV per U. So this is the rest energy of uranium-235, and to find the fraction, we just divide 200 MeV by the expression over here. And we should get an answer of about 1/1100.
Welcome to Brain Vision.
So for this question, we are assuming 100% efficiency for our nuclear fission reaction to be transmitted into the power of a house. Now the house requires 960 watts of power, and we want to find out how many fission reactions is required to power it for a year. Right, so the energy required in a year, we take 960 watts, multiply that by the number of seconds in a year. That is 3.156 times 10 to the power 7 seconds. Right, and this will give us the amount of energy that's required in terms of joules. But our energy for the fission is given in terms of MeV. So we're going to convert this into MeV. Right, so this will be in terms of MeV. So number of fissions required. We just have to take the energy required in a year, and we divide that by the energy released per fission, which is 200 MeV. Putting it into the calculator, we should be able to get the number of fission reactions, but what we want to really find is the mass, right? The mass of uranium-235 that's required. So the mass of uranium-235, since we know that each fission reaction requires one uranium-235 nuclide, we can just take the number of fissions and then we divide that by Avogadro's number, Avogadro's constant, to get the number of moles. Then we multiply this by the molar mass. And molar mass is given as 0.235 kilogram per mole. Alright, so putting everything together should be 960 watts. Multiplied by right, and this should be our final expression, which we will just need to evaluate in the calculator, and we should get a value of 0.37 grams, and this will be the mass of uranium-235 that's required.
Welcome to Brain Vision.
So for this question, we are assuming 100% efficiency for our nuclear fission reaction to be transmitted into the power of a house. Now the house requires 960 watts power. And we want to find out how many fission reactions is required to power it for a year. Right, so the energy required in a year, we take 960 watts, multiply that by the number of seconds in a year. That is 3.156 times 10 to the power 7 seconds. Right, and this will give us the amount of energy that's required in terms of joules. But our energy for the fission is given in terms of MeV. So we're going to convert this into MeV. Right, so this will be in terms of MeV. So number of fissions required. We just have to take the energy required in a year, and we divide that by the energy released per fission, which is 200 MeV. Putting it into the calculator, we should be able to get the number of fission reactions, but what we want to really find is the mass, right? The mass of uranium-235 that's required. So the mass of uranium-235, since we know that each fission reaction requires one uranium-235 nuclide, we can just take the number of fissions and then we divide that by Avogadro's number, Avogadro's constant, to get the number of moles. Then we multiply this by the molar mass. And molar mass is given as 0.235 kilogram per mole. Alright, so putting everything together should be 960 watts. Multiplied by right, and this should be our final expression, which we will just need to evaluate in the calculator, and we should get a value of 0.37 grams, and this will be the mass of uranium-235 that's required.
Welcome to Brain Vision.
In this question, we're looking at this particular fission reaction of uranium-235. Now the first part, we want to find how many neutrons are being produced as the end product. And to do that, we need to look at the conservation of nucleon number. So the nucleon number must be the same on the left hand side as well as the right hand side. So on the left hand side, we have a total nucleon number of 236. On the right, we should have 236 as well. So what we do is we take 236 minus 133, minus away 98, and we get a remainder of 5. Right? So the neutrons must give a total of 5 nucleon number, and that means that there must be 5 neutrons. To calculate what is the energy that's released, we look at the Q value. That is, we take the change in the mass of the nuclides, multiply that by C squared. The change in the mass means we take the initial masses, which is the mass of uranium plus mass of the neutron. We subtract away the mass of the final products, which is the antimony and mass of the niobium, as well as mass of the 5 neutrons. We multiply that by C squared. So all these masses you can look up online or through Appendix B for uranium. And this is for the neutrons. For the antimony, for the niobium, and that should be all the masses that we need, right? The neutrons have the same masses. We can use C squared in the form of 931.5 MeV per U, since we are dealing with atomic mass units, and it'd be more convenient to get the energy in terms of MeV. The final answer we should get is 171.1 MeV.
Welcome to Brain Vision.
Now, from previous questions, we know that uranium-235 releases energy about 200 MeV per fission reaction. We want to find what is the mass of uranium-235 required to produce a total energy of 3 times 10 to the power 7 joules. So first off, we need to find what is the number of fission reactions that is required. So we take 3, take the total energy, divide that by the energy per fission, which is 200 MeV. But we will have to convert them into the same units, so we convert MeV into joules. Right. This will give us the number of fissions, which is also equivalent to the number of uranium-235 that's required, since each fission reaction takes up one uranium-235 nuclide. So from here, we can find the mass of uranium-235 that's required. We just take the number of uranium-235, divide that by the Avogadro's constant. This will give us the number of moles, and then we multiply that by the molar mass, which is 235 kilograms per mole. So substituting everything in, we should get a value of 3.7 times 10 to the power minus 7 kilogram. Right? This is way smaller than the mass of the coal that is required, right? Which is 1 kg.
Welcome to Brain Vision.
In this question, we are given a neutron. Starts off with energy E0 of 1 MeV. And we want to find how many collisions it takes to bring it to an energy of 0.04 eV. Now we are given that for each collision, the energy is halved, right? 1/2 of its kinetic energy is lost to the collision. So the energy at the nth collision, after n collision, will be equals to the original energy multiplied by 1/2 to the power of n. So in order to find what is the number of collisions when En is equals to 0.040, right, we have to do some manipulation, right? So what we do is we bring E0 over to the right hand side, get half to the power of n. We take the logarithm, natural log on both sides. The power is brought down. Right, and finally we divide ln half over to the right hand side and we evaluate the expression. Should get n to be equals to 24.58. Now this is the minimum number of collisions that is required, but we know that number of collisions should be an integer value, so we will need to round this up to about 25 collisions, right? A minimum of 25 collisions to bring it below 0.04 EV.
Welcome to Brain Vision.
Now, in this question, we are given a nuclear reactor has an output of 950 megawatts. Now we're given that the efficiency of this reactor is 34% efficiency. So it means that the energy that is actually required to be produced is 950 megawatts divided by 0.34. Which is in fact 2,794 megawatts. Right? So this is the actual energy that's required to be produced. Now we know that for uranium-235, the energy released per nuclei, that is per fission reaction, is equivalent to 200 MeV. So from here we can find out what is the number of nuclei that is required by dividing 2,794 megawatts divided by 200 MeV. But the time scale that we're looking at is 1 year, right? So we have to multiply this by the number of seconds in a year, which is equals to 3.156 times 10 to the power of 7 seconds. So this will give us the amount of nuclei that is required to power the nuclear power plant for a year. But of course we have to convert the units of MeV into joules, since watts is in terms of joules per second, right? So convert to joules by multiplying by 1.6 times 10 to the power minus 13 joules per MeV. So from here we can get the mass. The mass of uranium-235 that we have, we just take the number of nuclei, we divide that by Avogadro's constant, which will tell us what is the number of moles of uranium-235. Then we multiply this by the molar mass, which is 0.235 kilograms per mole, right? And the final answer, we would get 1100 kilograms.
Welcome to Brain Vision.
In this question, we are assuming uranium-235 breaks up into 2 equal fragments. So in this case, we have 2 nuclides with nucleon number of 236 divided by 2, and that is 118. So 118 nucleons in both fragments. You want to find what is the electric potential energy as they just separate. So I'm going to assume that they are just touching. So what we will need is the distance, right, between the centers of these two spheres, and we can estimate that by taking the radius, right, 2 times of the radius of these 2 nuclides. The radius can be found by estimating using R0 times a to the power 1/3, where a is the nucleon number and R0 is the constant, 1.2 times 10 power minus 15 meters. So this is the estimated radius. Then we can find the potential energy, which is given as 1/4 pi epsilon naught Q1 Q2 over R, and the Q in this case will be equals to half that of the number of protons in our uranium. So uranium has 92 protons, divided by 2, we should have 46 protons each. So the charge should be 46 times the elementary charge. And the R in this case should be 2R, right? The distance between the two centers. So all we have to do now is just substitute the values in. Q, remember, is 46 square times the elementary charge squared divided by 2 times of R0, which is 1.2 times 10 to the power minus 15 times a to the power of 1/3, where a is 118. Right. So epsilon naught is the permittivity of free space, which you should be able to look up online. The value, which is about 8.85 times 10 to the power minus 12. So evaluating this expression, you should get a value of 4.16 times 10 to the power minus 11 joules. And converting that into MeV, right? Since we want to compare with the fission energy, which is 200 MeV, we have to divide this by 1.6 times 10 to the power minus 13 joules per MeV to give us about 260 MeV. From here we can compare with the fission energy, right? That is 200 MeV. So the potential energy is about, by taking 260 divided by 200, you get about 130 or 1.3. So that is about 130%. So it tells us that the potential energy is 30% larger than the fission energy release.
Welcome to Brain Vision.
In this question, we're going to find what's the increase in the rate after 1 second for our fission chain reaction. Now we are given that a multiplicative factor, let's call it F, of 1.0004. What this tells us is that after each fission reaction, it will release an average of 1.0004 neutrons that will actually go on to create further fission reaction. So in fact, this tells us, right, what is the increase in the rate after each cycle of chain reaction. Now to find out what is the total increase in the rate after 1 second, we will need to find out how many cycles there are. So the number of cycles that will happen in 1 second, we take 1 second divided by the time between each cycle, that is given as 1 milliseconds. So that's 10 to the power minus 3. So we should get 10 to the power 3, sorry. So this is the number of cycles that will occur in 1 second. To find out what is the increase in the rate, right, since we know that with each cycle the rate will be multiplied by this factor, so the final rate, so let's say we have an initial rate of R, the final rate will be R times F to the power of the number of cycles, right, which in this case is 10 to the power of 3. So this is the factor in which is increased, right, in which the rate is increased. So we just have to evaluate what is 1.0004 times 10 to the power of 1000, sorry, and we should get a value of 1.5, and so the rate will increase by 1.5 after 1 second.
Welcome to Brain Vision.
Hi everybody, so we want to know the kinetic energy of protons at the center of a star and we're given a temperature of T equals 2 times 10 to the 7th Kelvin, and we can use the kinetic energy formula that uses temperature, and that's going to be 3/2 times, well, K, and that's the Boltzmann constant, indeed, and I can write that here, that this is Boltzmann. Oops, let me correct the Z here. There we go. That's the Boltzmann constant. Okay, and so here we can just plug and chug. The Boltzmann constant is 8.625 times 10 to negative 5 eV K times 2 times 10 7 K equals, and you put all this into your calculator, and you're going to have a kinetic energy of 10 times 3 eV. And that is your answer.
Welcome to Brain Vision.
Hi everybody, so this question is basically asking us to prove that this reaction's energy release is 17.59. So we're just trying to prove that. And then we're given the reaction of the deuterium plus 3,1H. Let me go over here for helium plus the neutron, and there we were given 17.59 V, okay? And so with this, we can just find the energy released, and that's going to be MH plus MH, okay, minus ME, which H is hydrogen, by the way, minus M neutron times C squared, okay? Now we're going to do their masses, atomic masses of 2.014102 plus 3.01604 minus 4.00263 minus 1.0086665 times C squared. This equals 0.01883 UC squared times, because we need an MEV, 931.5 MeV, and we have U and C squared down here. And we know this crosses out, and that's going to equal 17.589 MeV, or if we round it up, 17.59. So that means we proved it.
Welcome to Brain Vision.
Hi everybody, so we need to show that the energy released when two deuterium nuclei fuse is 3.27 MeV. So we want to prove that is 3.27 MeV, and we have the reaction, so the two deuteriums, so 218 hydrogen, 3 to helium plus the neutron. And here we have E, M, H, and we're just going to times it by 2 because there's 2 here, minus M, H, E, and this is atomic mass, minus neutron, okay? And now we can just do plug and chug, and we round that out a little bit for parentheses, 2.0141102 minus 3.01609 minus 0.8665. And I'm just going to bring the U out, and there's a C squared. And so it's going to be 0.00351 U C squared times 931.5 MeV over UC squared. Okay, and what we can do is cross this out because we don't need those units, and the units cancel, and we end up with 3.27 MeV. So that means we proved it. So thank you guys.
Welcome to Brain Vision.
Hello everyone, I'm doing problem 30 of chapter 31. This question concerns the proton-proton chain, which is a fusion reaction describing the energy output of our sun. So the question refers us to formula 31.6, which I've reproduced here, which gives us 3 reaction equations that describe the fusion process. And each one has each reaction here is associated with a release of energy given in brackets here. And this released energy is, in fact, the Q value that the question is asking us about. So we're also given some values from the appendix, which I'll discuss in a moment. And we know that Q, the energy, is associated with delta M, which is the difference of mass between the elements or the items on the right side of the arrow and the mass of the elements or the components on the left side of the arrow, multiplied by the speed of light squared, c squared. So for this problem, we're basically budgeting energy, and we can rewrite these reaction equations in terms of Q here. So let's start. Write the Q value for A. So we're going to do the masses, the energy associated with the masses on the left side minus those on the right side. So here we have 2 protons. Let's say 2m sub p multiplied by c squared minus the mass of deuteron sub d times c squared minus the mass of the positron, which is in fact equal to the mass of the electron, by c squared. And the neutrino doesn't have an atomic mass, so it doesn't show up in this equation. And now we can see the c squared is present in every term, so we can factor that out. So I'll just quickly rewrite this. And now we want to look at our numbers from Appendix B to fill in the values. So I will convert to text for readability. And we want to be careful here because the text of the textbook tells us that we're dealing with nuclei here. So we don't want to take the H quantity because that includes an electron. So here we really want the mass of the proton. X means times. And this is given to us in atomic mass units U, and we always want to be sure to mark the units because they can really keep us from making mistakes. And we'll take the deuteron. And the electron mass. Oh, already forgetting my units here. We want all of this to be multiplied by c squared. And now you'll note that our units are in atomic mass units times c squared, whereas our final answer, we're looking for it to be in mega electron volts. So we'll need a conversion factor, which is 931.5 electron volts per c squared per u. And so you can check that the units all cancel out to give us the result in mega electron volts. And you can put that into a calculator and verify that it does in fact equal close to 0.42 mega electron volts. Equals approximately, I'll do a curly equal here. Now for B, we proceed in a similar way. we'll rewrite our equation, our expression for Q by subtracting the items on the right side of the arrow from those on the left side. Now, you'll notice that this time I'm marking M sub H for hydrogen, and I will explain that in just a moment. Plus a mass of deuteron, but again, I'll put deuterium instead of M sub D as I did up here. This is isotope of helium. So before we fill in the numbers, just a subtlety here. We're dealing with nuclei, but for the case of helium, which I'm sorry is cut off here, but I'll enter the values in a second and you'll see them. But for the case of helium in the appendix, we are only given the atomic mass, which includes electrons. But since electrons in this equation are balanced, that is, the nuclei on the left side of the arrow are each associated with an electron. So this side, there's, if we're including electrons, we have 2 electrons, and the nuclei over here is also associated with 2 electrons. So we can add 2 electrons to both sides of the equation and they cancel out. So that's why we were considering the mass of hydrogen here and not just the mass of the proton. Similarly for deuterium instead of just deuteron. So let's fill in our numbers. Oh, and again, gamma doesn't factor into the mass part here. Minus the mass of helium, which is 3.016029 atomic mass units. We'll multiply all of this by c squared, and again by our conversion factor to get mega electron volts. And again, we can put this into a calculator and obtain a Q similar to 5.49, or essentially 5.49. Great. Now for the final equation, let's do C. Again, write our expression for Q. We have 2 times the mass of this helium isotope. Minus the mass of helium, times C squared, minus the mass of helium. Minus 2 times the mass of hydrogen, where again we note that the electrons are balanced here, so we can add the electrons and subtract them here. So we will take the mass of hydrogen. Let's fill in the values with Appendix B. I'm just going to, hopefully you don't get confused, I'm going to try to enter them here, just for the sake of visibility up above. Minus 4.002603 U minus 2 times 1.007825 U. Again, multiply everything by C squared and by our conversion factor. And putting that into our calculator, we should get a Q value. Sorry, it's a little bit cramped here. A Q value of 12.86. Mega electron volts.